Hello everyone, and welcome to this series on complex analysis. In this series, we're going to be focusing on the very important, very beautiful, and also very curious and strange properties associated to complex numbers and the set for which they belong to. So, the very first thing that I want to discuss is the square root of -1, which you probably have already been introduced to in one of your undergraduate or basic courses. So, firstly, the square root of -1 does not belong to the set of real numbers. This is the very first important property associated with complex numbers. So, how would you prove that the square root of -1 is not a real number, hensing the potential motivation that a new set of numbers needs to be created? So, let's actually prove this by contradiction, and if you want to see if you can prove this on your own, feel free to do so. So, let's assume, for example, that the square root of -1 does belong to R. If that is true, then that means there exists some number x in the set of real numbers, such that when you square x, that is going to give you -1, and that comes from the definition of square roots. But what do we know about real numbers? But for all x in the set of real numbers, we know that x squared is always greater than or equal to 0. And from the field axioms for the set of reals, that's actually very, very easy to prove. And keep in mind 0 is strictly greater than -1. So if that's the particular case, that's going to give us a contradiction because x squared cannot be strictly greater than -1 and equal to -1 simultaneously. So that means that x does not belong to the set of real numbers, which means also, as a result, the square root of -1 also does not belong to the set of real numbers as well, right? So we get that particular result. So if this object does not belong to the set of real numbers, that means we have to define a new object. So what we're going to do is we're going to define the square root of -1 to be equal to this new object, I. And some people will refer to this object as the imaginary unit of the set of complex numbers. So, what do we get in return when we define this new object? So when we define this new object, say the square root of -1, it allows us to do a lot more evaluations of expressions. Obviously, the square root of -1 is now defined to be equal to something. We can also define the square root of -4, -9, and other minus numbers as a result of it. Because the square root of -4 can be represented as the square root of 4 times -1, and then we can hopefully distribute square roots over these two numbers, and we're going to have the square root of 4 multiplied by the square root of -1. We already know that the square root of 4 is defined to be equal to 2, and the square root of -1 is now defined to be equal to I, so we can say hopefully that the square root of -4 is equal to 2I. But keep in mind, we have not really explored the properties that this new object has, so it's possible that we do get some contradictions if we try to assume that all of the properties of the real numbers are sort of inherited in this new set of objects. As an easy example to sort of illustrate this property, let's assume that we have the square root of 4, for example. I think everybody can agree that the square root of 4 can be represented as the square root of -2 times -2, because -2 times -2 is positive 4. So now what I want to do is I want to re-represent this as the square root of -2 times the square root of -2, assuming that we can actually distribute square roots over these numbers. Because keep in mind, in the set of real numbers, these two objects are not defined, but now we have some way of defining them. So maybe the square root of 4 can be represented as such. If we accept that this is indeed true, what you're actually going to get is we're going to have the square root of 2 times the square root of -1, the square root of 2 times the square root of -1. The square root of 2 times the square root of 2 is going to be equal to 2, assuming that we can commute these objects. Also, the square root of -1 times the square root of -1 will be equal to I squared. And if we take the square root of -1 to be equal to I, some people will say that an equivalent definition to this is that I squared will be equal to -1. So if we take I squared to be equal to -1, then what we have is this is just going to be equal to 2 times -1. Now we're in the set of real numbers completely, which is going to be equal to -2. So we have that the square root of 4 is equal to 2, but we know that this actually should be equal to 2, and 2 and -2 are not equal to each other. So we get a contradiction. right? So we get a contradiction, meaning that we cannot distribute over negative numbers when it comes to square root multiplication. Now, although it does give us a contradiction, there is something that's actually very, very interesting to look at here. So if we look at the set of real numbers along a horizontal axis x, and we look at 0 here, minus 2, and positive 2 here, and let's assume that the problem that we're interested in is the square root of 4. We already know that the square root of 4 is equal to 2. But if we distribute square roots over this product of negative numbers, what it actually does is it rotates the solution 180 degrees counterclockwise into minus 2. And we could rotate that incorrect solution another 180 degrees to get back positive 2. So although negative 2 is an incorrect solution, there is some geometric nature associated to it when it comes to rotational symmetry. And in this set of complex numbers, there's actually a very beautiful geometric structure going on underneath it when it comes to multiplication by complex numbers, which we will definitely get to. Now, before we dive into those beautiful objects, we first need to start defining how these new objects that contain I will interact with one another and also the set of real numbers that are already defined. So let's start off by taking A, B, C, and D to all be real numbers because we already know how those will interact with each other because the set of real numbers is a field, which means, you got associativity, commutativity, distributivity, additive inverses, multiplicative inverses for non-zero numbers. And let's also consider this new object I, which is defined to be equal to the square root of minus 1. So let's consider a couple basic operations. So the first operation that we're going to consider is when you take a real number, let's assume that this is A, multiplied by a number, let's assume this is, say, BI. So BI is the product of a real number B and this new object I. So we're going to be defining this to be equal to AB, so the real numbers multiplied together, times I. So the next object that I want to look at is if we have, for example, AI plus BI. Right? So keep in mind we have this particular object A. Keep in mind that's in the set of real numbers. We have this particular object here, which is not in the set of real numbers. And we get this particular object here, which is also not in the set of real numbers. So here, again, we have an object that's not in the set of reals. We have an object not in the set of reals. So what is this going to be? And of course, if A and B are equal to 0, then of course it is in the set of reals, right? But generally speaking, it's not. So we're going to define this in a way such that it sort of makes sense in terms of operations. So if I is kind of like a variable, then hopefully we would like to combine like terms or something like that. So a reasonable way of defining AI plus BI would be equal to doing A plus B, the quantity, times I, right? So now we have another object, and again, that would not be in the set of reals. So we have these little baby objects, but now we can scale them by a factor of a real number, and now it's going to make sense. So that's how you add these particular objects, but what about multiplying? So if we have AI times BI, what would be a reasonable way to define this? So maybe we would define this in a similar way like we did with the reals. We would take these A's and B's and reassociate them, so that would be A times B, and then we would multiply that by I times I. So when we do that, what do we get? So we have AB multiplied by I squared, and I squared we already know is going to be negative 1. So that would just be equal to the opposite of the product AB. Now what's very interesting here is if you have an object here that's not in the set of reals, you have an object here that's not in the set of reals, when you multiply them, it's possible that you actually do get an object that is in the set of reals because A and B are real numbers, and the real numbers is closed under multiplication and negation. So we have that the product of these two new objects actually results in an object that is indeed real, right? So there is some very beautiful connections between these set of real numbers and these new objects. So if we consider other operations, for example, what if we have like A plus BI and then added to C plus DI? What would be a reasonable way to define this? Well, maybe we can combine like terms because those don't have i's in them, and those terms do have i's in them. So a reasonable way to define this would be, say, A plus C, so the things that don't have i's, and then B plus D multiplied by I. right? So now we have addition defined, and we can similarly define subtraction in a very similar way. So what about multiplication of these more structural objects? So what if we have a plus bi multiplied by c plus di? What would be a reasonable way to define this? So this is kind of motivating some sense of distributivity between reals and these new objects. So maybe we can define this as the following. So maybe we can do a times c, ADI, and then BCI, and then BDI squared. So when we define it this way, what do we get? So this is going to be equal to AC plus AD plus BC, the quantity I, and I squared is equal to minus 1, so we can write that as minus BD, and then we can write this as AC minus BD, and then plus AD plus BC, the quantity I. And then this gives us the similar structure. Here's a real number, and here's this new object for which we're defining. So everything actually comes out very nicely. So we have addition, we have subtraction, we have scalar multiplication. So all that's left to really deal with is division. And division can sometimes get a little bit tricky, so let's see how that would turn out. So let's assume that we have a plus bi all over c plus di. What would be a reasonable way to define that? But keep in mind that I is equal to the square root of minus 1, so this is kind of like a radical expression, 1 plus the square root of 2 divided by 3 minus the square root of 5. Like, how would you, rearrange this particular object? So we have this particular same structure, real number plus real number times new object. So, similar to how we did with rational expressions, we can multiply top and bottom of this maybe by a conjugate, for example, c minus di. And let's see actually how that evolves. So now we're multiplying two objects of similar structure on top and same on bottom. So when we do that, what are we going to have? Well, we're going to have AC minus ADI plus BCI, and then minus BDI squared would just be positive BD. And on the bottom, we're going to have C squared minus CDI plus CDI, and then minus DI squared would be positive D squared. So what we have here, which is actually very, very interesting, is that these two objects vanish and we can cancel them. And then we're just going to be left with c squared plus d squared on the bottom, which is just a real number. So when we have simplified this and then we regroup the top in the similar manner as before, we're going to have AC plus BD divided by c squared plus d squared, so that's a real number. And then we're going to have on the top BC minus AD all over c squared plus d squared, that's a real number, multiplied by I. So now we have defined scalar multiplication, addition, subtraction, multiplication, and division of these new objects. So this allows us to say, okay, maybe we can define a new set of numbers that pretty much has this type of structural interaction between the real numbers and this new object for which we have defined as I. So let's define our new set of numbers, and sometimes the set is called the set of complex numbers. So the set of complex numbers is given by the following. So most of the time people denote the set of complex numbers by this fancy letter C. And this is the set of all objects of the form Z, where Z can be represented in the form x plus iy. Some people write x plus yi, that's also okay, where x and y are real numbers, and I is this newly defined object, minus 1. Right? So up to this point, we have defined, okay, if we were to take any two objects from, for example, Z1, Z2, and Z3 from this particular set C, we have already defined how we would do, for example, Z1 plus or minus Z2, Z1 times Z2. We know how to do Z1 divided by Z2, and we also know how to do scalars times complex numbers as well, for example, C times C. So everything is lovely and well defined. So is there any structural property associated with the complex numbers that's similar to the set of real numbers? And indeed there is. So the very first theorem that I want to mention, and I guess this was theorem 2 because we already proved that square root of I does not belong to R, and it's that C is a field. right? So C is a field, just like the set of real numbers. And what if you don't remember what a field is? So a field, if you want to prove this, so a proof outline, using the definitions that we already have done for addition, subtraction, multiplication, division, and scalar multiplication, you would have to show the associative property holds. So the associative property holds for both operations, multiplication and addition. So you would have to show that, for example, z1 plus z2 plus z3 is equal to z1 plus z2 plus z3. You would also have to show that z1 times z2 times z3 will be equal to z1 times z2 times z3. And again, as long as you work with those definitions that we did for addition and multiplication of complex numbers, you should be able to justify these as long as you assume that the set of real numbers are associative and commutative and all of those things. So the commutative laws also hold for the set of complex numbers with those definitions of operations. That is, if we do z1 plus z2, you're going to get the same exact value as if you do z2 plus z1. If you do z1 times z2, you will get the same exact answer as if you were to do z2 times z1. So those are your commutative laws. The third sort of combines addition and multiplication into the same realm. That would be your distributive property. That is, if you do z1 times the sum of z1 and z2, you will just get z1 times z2, and that should be 2 and 3. So z1 times z2 plus z1 times z3. Some will also do a right distributive law as well. But that's actually easier to prove if you assume commutativity already holds. And then the fourth would be identity existence. And you should be able to show that the identity element in this particular object, some people will represent the identity element as e. I is already reserved for, the square root of -1, 0 plus 0 I. And you should be able to show that, for example, e plus z equals z plus e is equal to e, and that's going to be true for all z inside of C, and also the existence of inverses for objects. And that says, for example, there exists, for example, a w such that z plus w equals w plus z equals 0 for addition, and also w such that z times 1 over w will be equal to 1, provided that z is not equal to 0, and that's not equal to w. Right? So multiplicative inverses and additive inverses exist. So if you can show all those things for the properties of real numbers, then we now have that the set of complex numbers is indeed a field. So now that we have the set of complex numbers defined and we have the tools in order to show that the set of complex numbers is indeed a field, let's introduce some of the functions that are actually unique to the set of complex numbers that don't really make sense in the set of real numbers. So let's assume that we have some complex number z that's of the form x plus iy. The first function that's unique to the set of complex numbers is the following, and let's denote it by re of z. So re of z is going to be defined to be equal to x. Another function is im of z, and this is going to be defined to be equal to y. So some people will call re the real part of z, and imz is sometimes referred to as the imaginary part of z. And obviously both of these functions, for example, re maps c to r, and similarly, imaginary part will also map c to r, right? So those functions return the real and the imaginary part of a complex number. Another function that is useful in the realm of complex variables is the conjugate of z. Some people also write this as z with a bar over it, not to be confused with averages. So what is z? Well, z is again x plus iy, and this is usually defined to be equal to x minus iy. So the real part stays the same and the imaginary part negates. So that's what we call the conjugate, or some people will say the complex conjugate of the complex number z. And another calculation or function on the set of complex numbers is sometimes abbreviated by this, similar to the absolute value, and this is defined to be equal to the square root of x squared plus y squared. And some people refer to this as the modulus. Some people also call it the length or the norm of z. Now, what exactly does this represent? So if we have z is equal to x plus iy, and let's assume that we put, for example, the real part of z on the horizontal and the imaginary part of z on the vertical axis, and let's assume that we have, for example, the point x comma y in R2, for example, then if we sort of graph this particular vector, then we're going to have that this represents the length of x, because this corresponds to x and this horizontal component corresponds to y. So what's interesting in this representation is that, keep in mind, z is a particular complex number. It's in some sense a one-dimensional object, but how I have it graphed here is a two-dimensional representation of a one-dimensional object, because we have a real part, an imaginary part, that represents one complex number. So the point xy, which, keep in mind, belongs to the set R2, and the object, which we denote by z, which again is an object in C, are similar to one another in terms of their structure. Some people will say that R2 and C are also similar in terms of structure from the set theoretic perspective. Some people also throw out words such as these sets are isomorphic to one another, which we won't get into. That's more of an abstract algebra conversation, but they are similar in some sort of ways, right? Because you keep in mind, I need to give you two real numbers in order for you to tell me which complex number I am talking about, right? But these are four different functions that are definitely unique to the set of complex numbers. That is the real part, the imaginary part, the conjugate, and the modulus of a complex number. But there's several other functions out there that are very, very useful, and I'll define the next one in a different set. For example, let's just call this definition 3. And what we're going to do is we're going to let theta be a shorthand version for arg of z. So this is going to be representing the argument of the complex number z. So if we sort of go back up to this picture, theta is going to be this angle right here, the angle that that associated vector makes with respect to the horizontal or real axis. So from the tangent perspective, we see that if this picture is indeed valid for a particular complex number z in quadrant 1, then the tangent of theta will be equal to y over x. But if you rotate that theta into, say, quadrant 2, 3, or 4, then it's a little bit more tricky to deal with. So let's actually be very, very careful on how we define theta for different numbers z. So for 3.1, we'll define the classical or basic one. So theta will be equal to the arctangent of y over x if x is strictly greater than 0 for any value of y. The second variation will be equal to theta is equal to the arctangent of y over x. And we're also going to add pi to this if x is negative and y is positive. Now the next one, you might want to pause the video and take a guess of what this is going to be. So theta will be equal to the arctangent of y over x minus pi if x is less than 0 and y is less than 0. And some people will include equality on the second variation for that. Right? So we have that particular result. So we have x positive, any y. We have x negative for y positive. We have x negative for y negative. Now we need to consider when x is equal to 0 because we have our positives and our negatives covered. So the next two, for example, theta will be equal to something if x is equal to 0 and y is greater than 0. 3.5 will be theta will be equal to something if x is 0 and y is negative. Do you want to take a guess of what we define theta to be in these cases? So theta will be equal to pi over 2 for the first case and negative pi over 2 for the second case. And there's one other case to consider. Do you know what case that is? So the last case will be the case if x and y are both equal to 0. And you might want to pause this video and think, what would you define theta to be? So if x and y are both 0, that means the point representation of z is the origin, and which means that vector doesn't have any magnitude. So what direction is that vector pointing in? Well, it's not actually pointing in any direction, or it's pointing in all directions. So for x equals y equals 0, we usually say that theta will be undefined for that particular representation, right? So that's the argument of a particular complex number and how we define it. So now that we have some of the principles associated to complex numbers established, there's another representation that is actually very useful when analyzing complex numbers. Keep in mind that the complex numbers are a one-dimensional structure, but they're very similar to a two-dimensional structure with the set of real numbers. So maybe we can use some of the two-dimensional representations of R2 and use them to represent things that belong to C1. In particular, we can represent any pair of numbers in R2 with respect to Cartesian coordinates, which is typical with x, y, and also polar coordinates, which is with respect to r theta. Well, r is the length of that hypotenuse for that associated right triangle. So if you remember, there are some very important connections between these particular objects. In particular, z, which let's assume is of the structure x plus I, y. If we replace x and y with their associated polar forms, then this form, which is sometimes called the standard form of a complex number, can be rewritten in another form, because x plus I, y will now be equal to, x is going to be r cosine theta, and y will be equal to r sine theta. So we have this particular object, and we can factor out thus r out of this expression, and we're going to have r multiplied by cosine theta plus I sine theta. And if you remember from single variable calculus or maybe some other courses, cosine theta plus I sine theta, and some people write this as CIS of theta, not really used as much anymore, but is still present in some literature. This is actually equivalent to exponential functions, because if you recall, that cosine theta plus I sine theta is actually equal to e to the power of I theta. And if this looks very new to you or strange to you and you know Taylor series for functions, use the Taylor series for cosine, use the Taylor series for sine, and use the Taylor series for exponential functions. Plug in e, rearrange, and simplify, and you will get this beautiful identity. Some people will call it the Euler-Cotes identity. So that means x plus iy is actually equal to r e to the I theta, right? Here, r is going to be the magnitude or the modulus of the complex number, and theta obviously is going to be equal to the argument of the complex number. So therefore, we can write this particular object, and sometimes people will call this the polar form of z. So we can say that z, aka is equal to x plus iy, the standard form, is actually going to be equal to the norm of z times e to the I arg of z. Right? So we have this standard form and this polar form representation of complex numbers. Now, there are several different theorems and cute tricks that you can pull with the polar form of complex numbers. One of the very important theorems that you probably should know is associated to de Moivre. So the de Moivre theorem for complex numbers states that if you have cosine theta plus I sine theta, and you exponentiate the sum to the power of n, where n is some real number, what you will actually get is cosine of n theta plus I sine of n theta. And you might be looking at this and say, oh, that's actually kind of strange, because what we're actually doing here is we're foiling or distributing n inside of a sum and inside of the trigonometric functions to get this particular object. And you're like, that's not how math works. Is this indeed true? And indeed it is. So maybe you want to pause this video and see if you can prove this identity for what we know. So what do we know? So the cosine theta plus I sine of theta, raised to the power of n is going to be equal to what? So let's look at the polar representation of cosine theta plus I sine theta, and that's just going to be equal to e to the power of I theta raised to the power of n, and by powers of exponents, that's just going to be equal to e to the I n theta. Now, n theta is now just the argument of a new complex number, and that new complex number by the Euler-Cotes identity will just be equal to cosine of n theta plus I sine of n theta, which is indeed the de Moivre theorem for complex numbers. So what can you use these cute tricks for? So let's actually look at a fun numerical example of this. Let's see if you can figure out what 1 plus I to the power of 28 is equal to. And if you want to try this exercise out on your own, before I show you the solution, please feel free to try it on your own. So what is this? So I'm going to look at the real and imaginary parts for this. So the real part is equal to 1, the imaginary part is equal to 1, so the complex number 1 plus I, so 1 plus I, is going to be located here. So therefore the norm of 1 plus I will be equal to the square root of 1 squared plus 1 squared, which will just be equal to the square root of 2. So that's going to be equal to our R. And since the length and the height of that particular triangle is equal to each other, that means that angle right there is going to be 45 degrees, or pi over 4 radians. Okay, so that's going to be the argument of the complex number 1 plus I. So now let us take a look at 1 plus I to the power of 28 and see what we get. So 1 plus I to the 28 is going to be equal to what? So what I want to do is I want to write that in complex notation form. So that's going to be equal to r e to the I theta raised to the power of 28, and that's going to be equal to what? So r is equal to the square root of 2. So we're going to have the square root of 2 times e to the I pi over 4. And all of that is going to be exponentiated to the power of 28. We can distribute over multiplication for that power of 28. So we're going to have the square root of 2 to the power of 28 times e to the I pi over 4 times 28. Right? So that's actually very, very nice. So we have that. And keep in mind, 7 times 4 is 28, and 28 divided by 2 is 14. So we're going to write this as just 2 to the power of 14 times e to the, so 7 times 4 is 28, so that's going to be I 7 pi. Okay, so we have 2 to the power of 14. That's some big number which we can simplify later. So what do we have so far? So we have that 1 plus I to the power of 28. So from here we can use de Moivre Laplace, or actually just de Moivre on this particular object. And that's going to be equal to 2 to the power of 14 multiplied by the cosine of 7 pi plus I times the sine of 7 pi. Right? And keep in mind that sine and cosine are both periodic functions of both 2 pi, so we can subtract 2 pi's from each of these in order to simplify them. So if we subtract 2 pi from 7 pi 3 times, we're just going to be left with pi. So we have cosine of pi plus I times the sine of pi, and now we can simplify via our unit circles. So where exactly is pi? Well, pi is 180 degrees. That's going to be located right there, which is associated to the point minus 1, 0. Cosine is x, that's going to be equal to minus 1. Sine is y, that's going to be equal to 0. So the I term disappears, and then we're just going to be left with 2 to the power of 14 times minus 1. So we have minus 1 times 2 to the power of 14. So 1 plus I is equal to the opposite of 2 to the power of 14. And I guess we could simplify that and write that as minus 16,384 for our particular result. Right? So that's an application of the de Moivre theorem for exponentiating complex numbers that are very simple without actually multiplying 1 plus I by itself 28 times, distributing and combining like terms, and possibly making a mistake. So up to this point, we have a few properties that are actually very interesting about the set of complex numbers. We have new functions defined on them. There's definitely lots of things that are similar to the set of real numbers and also R2, the Cartesian product of reals with itself, with respect to the complex numbers. So one could ask, well, is there any real difference between, C and R in terms of just the objects that are inside of them? And actually the answer is yes. But before I spell out what a really big difference between these sets is, let's also review, what it means for a field F to be an ordered field. So we already know that R is a field, and we already have proven that C is a field as well. So we say that that field is ordered or orderable if there exists a relation, which I'm going to denote by less than or equal to, such that for all A, B, C inside of that field, we have these 5 relations that satisfy. So if A is less than or equal to B and B is less than or equal to A, then we have that A and B must be equal to each other. Some people refer to this as the anti-symmetry property of relations. If A is less than or equal to B and B is less than or equal to C, then A will be less than or equal to C. Some people refer to this as the transitivity property of relations. Then either A is less than or equal to B or B is less than or equal to A. Some people refer to this as the totality property. You may also see people sometimes write this as A is less than B, B is less than A, or A is equal to B, but we're looking at the relation less than or equal to, so we only have 2 cases to consider. And then we have if A is less than or equal to B, then A plus C will be less than B plus C. Some people will call this the translation invariance property of the relation. And if A is a positive number, which we write 0 is less than or equal to A, and B is also a non-negative number, 0 is less than or equal to B, then the product of A and B will also be non-negative. Some people call this the positive product of the relation less than or equal to each other. So why do I bring this up? So we already know that the set of real numbers R is an ordered field, right? So R is an ordered field. But what about C? So what about C? Now, if C was an ordered field, then that means we can pick any 2 complex numbers, for example, 2 plus I and 5 plus 27I, and be able to put a symbol in between them that represents some ordering. For example, is 2 plus I less than 5 plus 27I? You can be like, well, 2 is less than 5, so the real parts satisfy, and 1 is less than 27, so the imaginary parts must satisfy. So can we say that 2 plus I is less than 5 plus 27I? Does this even make sense as it did in the set of real numbers? Actually, no. You can't, right? So that means that's a theorem. That means I should be able to verify, that this is indeed true. So the theorem is that C is not an ordered field. So we already know that C is a field, so we don't have to pick apart that particular thing. So we just need to show that C is not orderable. Okay? So how are we going to prove this? And if you want to pause this video and see if you can do that, feel free to do so. So if it is, assume it is, so that means I'm going for a proof by contradiction, then properties 1 through 5 will satisfy for all, for example, x, y in C, right? In particular, 0, I, and minus I. So I'm going to focus on the additive identity, the complex unit I, and its opposite, minus I, right? So if I were to pick these 3, I should be able to order them with respect to these particular axioms. And if it is orderable, then axioms 1 through 5 will satisfy. Okay, so our first case, so case A, let's assume that 0 is less than or equal to I. Right? Our other case is that I would be less than or equal to 0. That's going to be case B because one of these must be true, right? And obviously I is not equal to 0, so we don't have to consider that case. Okay? So if 0 is less than or equal to I, then from that we can also see that 0 is also less than or equal to I. Yes, I'm just repeating myself, but for good reason. So Because I is one number and I is another number, so that means by property 5, because in this case we're assuming that they're non-negative numbers, so their product should be non-negative. So by property 5, we have that 0 must be less than or equal to I times I. But what's I times I? Well, that's just going to be equal to I squared, and I squared is equal to minus 1. But keep in mind, 0 and minus 1 are real numbers, and in the set of real numbers we have that 0 is less than or equal to 1 would give us a contradiction, right? So because real numbers are orderable and minus 1 and 0 are real numbers. So since we get a contradiction, we see that 0 is less than or equal to I is a false premise, right? So 0 cannot be less than or equal to I, right? So if it is an ordered field, that means that I must be less than or equal to 0. Because if the first isn't true, that means the second has to be true if this is indeed an orderable field, right? So if I is less than or equal to 0, where would the contradiction for this come into the picture? So if I is less than or equal to 0, then by translation invariance, we have that I plus minus I will be less than or equal to 0 plus minus I, right? So this is our translation invariance property of the ordering relation. And I plus minus I, that's obviously going to give us 0, and we're going to have the 0 is less than or equal to minus I. Right? So keep in mind that if 0 is less than or equal to I, and keep in mind there is another property that actually comes as a corollary, that if 0 is less than or equal to A and 0 is less than or equal to B, then 0 is less than or equal to AB, you should be able to show that this is actually equivalent to saying if A is less than or equal to B, that means A squared is less than or equal to B squared. Right? That would be a corollary of that. So if we take that as fact, which I will because that's more of a an ordering property from the reals, so you should be able to verify that it holds here, then you should be able to see that if 0 is less than or equal to minus I, then 0 squared will be less than or equal to minus I, the quantity squared. So what is 0 squared? Well, 0 squared will be equal to 0 is less than or equal to minus 1 squared times I squared by properties of exponents, and that's going to be equal to what? So we have 0 is less than or equal to minus 1 squared is 1, and I squared will be minus 1. So we have this same contradiction, right? So we have a contradiction, which means that I is not less than or equal to 0, right? So by property, what was it? Property 3. So by property 3, we have that 0 must be less than I is less than 0, or I is equal to 0 if we split it up into the two cases. But that's not possible. We already got a contradiction out of that. That's not possible. We already proved a contradiction out of that. And I is not a real number, so I can't be equal to 0 because 0 is real, so that doesn't make sense either, right? And any two numbers must be comparable in this set in order for it to be orderable, and we found some numbers where it actually breaks. So we have here that C is not orderable. In particular, C is not a ordered field, right? So that's kind of sad. So R is an ordered field, but C is not, but at least C is still a field even though it's not orderable. Right? So that's one of the very odd things about the set of complex numbers. But that's just an introduction to the set of complex numbers. There's definitely so many other beautiful things and also fascinating things associated with them, but we'll get into them in another day. So I hope you enjoyed this video, and I'll see you in the next one. Take care.